All right, so earlier, we had delta G standard is equal to minus RT natural log of K. That's the relationship between the equilibrium constant and the delta G. But now delta G, let's say delta G of the is equal to minus RT natural log of K. Let's say this is standard condition at the reaction, let's say. So what does this mean? So, what does this mean is the question. Well, again, it's about the relationship between delta G and the equilibrium constant. But equilibrium constant is what? It's something about it's a ratio, right? So equilibrium constant is a ratio of activity. I'm just going to put it product over reactant, activity of reactant. Notice that if you have multiple species, activity of product species A, activity of product species B, and so on. So you have multiple, but just for the sake of simplicity, I just have activity of product and activity of reaction. Now, that's the ratio. So keep that in mind. So you can call this, ratio, right? So these are the ratios, right? So now, so if the equilibrium constant is greater than 1, so that's what you hear. Again, if you have a multi-species system, you have, again, something like, you don't have to write this, but, activity of product D times activity of product C divided by activity of A and B, and so on. Oops, activity of B, so on. So keep that in mind. Now, that's it. Let's go back. You don't have to write this, all right? So equilibrium constant greater than 1 means what? This is, if you can call this, you have more product dominant, right? So it's a product, all right? So you can call them more products, all right? So more products at equilibrium. So which means, natural log of K is equal to positive or negative in this case. It's going to be always positive, right? Because again, greater than 1, natural log of greater than 1, it's going to be positive. So that means, so if that's the case, then end result is what? It's minus natural log RT, so minus RT natural log of K. And this part right here is positive, and then this part right here is negative. So negative times positive is going to be always negative, right? So in this case, delta G of the reaction standard condition in this case is equal to negative, right? So in this case, the reaction, I'm just going to use the abbreviation reaction, goes spontaneously, right? Reaction spontaneously move toward which direction? More toward the products, right? Right? So keep that in mind. So again, negative, its reaction is spontaneous. That's fine. Again, but depending on the magnitude of K, then more, so higher it is, more negative it's going to be, right? So again, equilibrium constant actually, is related to delta G. The energy is used to drive the reaction forward and more toward the product, so that you have more products at the end. Kind of interesting. So likewise, and then I'm going to erase this one. So then, likewise, so what does it mean? So let's leave this part out. Delta G is greater than 0, let's say, right? So that means you have equilibrium constant less than 1. So in this case, inherently, there will be less products, right? There will be less products, right? Or products, or product, depending on type of species you're dealing with. Wait, so less products because it's less than 1, so it's denominator is large, the ratio wise. So this part right here, it's more dominant. So reactant is more dominant, right? So wait, so but it's not 0. So in this case, wait, I'm just gonna call it wait. There are still product formed. Because otherwise, if this is 0, then K is going to be 0, right? Formed. So remember, still product formed because this number is small in this case. You don't have to write this one. And then this one's large. And therefore, you still have smaller than 1. Because if this is 0, don't write this though. If this is 0, then the whole thing is going to become 0, right? So keep that in mind. So now, so remember, so even if equilibrium constant is less than 1, or inherently delta G is greater than 0. So keep that in mind, right? So the more negative it is, also more positive it is. So you have higher the delta G. So inherently the reaction wouldn't go, but still product is formed. So reaction actually goes, but the difference is that it's reactant dominant. So in this case, the ratio in this case, you have more reactant. All right, so keep that in mind. Now, so still the reaction still goes, but it just doesn't go as much. So keep that in mind. Now, so delta G is delta G. So again, let me just write this down. Delta G is greater than 0. So what does it mean? So this means you call it non-spontaneous, right? Non-spontaneous, but it's spontaneous. Its reaction still goes, But remember, reaction, still, right? Results in some, right, product formation. So keep that in mind. Now, that said, all right, very little. I'm just going to call it very little, all right? But still does form, all right? Little, all right? So keep that in mind. Now, so of course, K, so that's K is greater, K is less than 1, G is greater than 0, but how about K is equal to 0? So delta G is equal to 0, let's say, right? Then, if equilibrium constant is equal to 0, because remember, natural log of K, or natural log of 0, all right? So that's bad. Like is equal to 1. The natural log of 1, right, is equal to 0, right? Natural log of 1 is equal to 0. So keep that in mind. So in this case, right? So then delta G is going to be 0 because minus RT, natural log of 1, which means this part right here is 0. So, is equal to minus RT times 0 is equal to 0, right? So delta G is equal to. So in this case, all right, so so in this case it's at equilibrium, but in this case that's very interesting because delta G is delta H minus T. Delta S is what we have been talking about, but at this point is equal to 0. So at equilibrium, all right, it's going to be 0. So what does it mean? So if this minus this is equal to 0, so you can call it delta H is equal to T delta S. And of course, T is equal to delta H over delta S, right? And you can call this delta H of the reaction over delta H of S of the reaction, right? So again, this is what we call, temperature at equilibrium, for standard condition. So keep that in mind, standard condition. All right. So, all right, looking good. So then what's next? All right, so of course, again, that's temperature. But speaking of temperature, I mean, in enthalpy, we talked about, enthalpy being temperature dependent. Oftentimes, we just consider a temperature, under the normal circumstances, under our biological condition, temperature change wouldn't affect the enthalpy as much. So how does the temperature affect the equilibrium, right? Effect of temperature, right, on equilibrium. So let's talk about this, all right? So from the earlier from natural log of k is equal to, I'm just going to write it in the minus delta g over rt. Just rewrite this, just take this on the other side, delta g over rt, and then of course is equal to delta g is equal to minus delta h over rt plus, and then delta s over r. Of course delta t delta s, but then divide by rt, so the whole thing. So you can just this can be the whole things can be rt, but then t cancels out. So I just separated the terms here. We're gonna call this equation 1, and then if the different temperature, so this is at so we call this at at t t degree Kelvin, all right? So at, let's say t prime Kelvin, then in this case we can just rewrite this equation again, natural log of k. I'm gonna call this equilibrium constant changes, let's say, and then is equal to minus delta h, and then we call this standard condition, by the way, delta s, standard, or delta s, well, standard condition, but anyway, delta h of the standard over rt prime, and then plus delta s of the r, because temperature cancels out in standard. All right. So then assuming that the delta H doesn't really change over the temperature range. Of course, it might. If that's the case, we have to accommodate that. But anyways, assuming that temperature delta H doesn't change, then so we call this equation 2. So making it 2 minus 1. So in this case, 2 minus 1 gives you well, let's just this minus this. So it's gonna be natural log of k prime minus natural log of k is equal to we can just combine these terms together. So delta h over r, and then and 1 over, what does it 1 over t minus 1 over t prime. Of course this minus that would be the same term, they'll cancel out. T terms is different, so we can just leave that here. Delta h and r is the same, I just took it out, right? So this is the relationship between the temperature change. So if you change the temperature, and then equilibrium constant changes. So so keep that in mind. So that's the relationship between the so this is the when the temperature changes, equilibrium constant changes. Of course, if this may not be the this if it doesn't change, then it's gonna be 0 anyway. So even if temperature changes, it's gonna be 0 if that's if it happens to be the same, if they don't change. So keep that in mind. All right. So what else? What else can I say? So I think that's pretty much it for temperature dependence. So we call this temperature dependence temperature dependence on equilibrium constant. So keep that in mind. All right. So I think that's pretty good. So this is the relationship between the equilibrium constant and the delta G. All right.